and is also an active participant in various research activities along with teaching and research projects. In addition to all these activities, he's also serving or acting as participating as a director of Techno Campus, which is an innovative and ambitious project that seeks to engage young people with computing and its related subjects. So, Professor, it's all yours now. So please.
Sorry, can you allow me to share my screen?
Tanveer, please enable screen sharing, Tanveer.
Hi, thank you for your welcome. It's a strange experience to be doing.
Can you give access to Dr. Andrew?
It says that I'm sharing my screen now.
Hamza, can you
see it?
Yes, Andrew, your screen is over there.
Brilliant.
We can see it. Yeah.
Brilliant. This is a very strange experience doing a webinar. It's my first webinar I think I've ever done. And I know that I've got friends in different parts of Pakistan that are watching today. I have friends in Turkey who's watching today, and I have family in Wales that are watching today. So it's quite a strange experience to be doing a webinar. I've been to Pakistan quite a number of times, 8 times in fact, since my first visit in 2015. And this week, I was hoping to be there for FIT 2020, but obviously because of COVID, again, that hasn't happened. So a lot has changed because of COVID. And while my research is a technical kind of research base, really what I want to do this afternoon, is the afternoon in Wales, is I'd rather talk a little bit about a personal impact assessment about what COVID has meant and done. My day job is as a professor of computing at the University of South Wales, and also as director of the Wales Institute of Digital Information to do with health research. And COVID has impacted significantly both those activities. Because of COVID, I've had more time at home, and I've used that time at home to do a reasonable amount of reading that sometimes I don't get time for. And one of the books I've read, or I should say reread, I read it when I was a student in school, is A Tale of Two Cities by a man called Charles Dickens, who's a very famous British author. And he starts off his book by saying these words: "It was the best of times, it was the worst of times." And as I think back over the last few months of COVID, it has indeed been the best of times, and it has been also the worst of times. I could have chosen many images to sum up the best of times and the worst of times, but I've just chosen 2. One of the pictures is of hands clapping. In the UK, we have a very good national health service where we have our medical services, we have our doctors, and we have our nurses, and we have our hospitals. And they have fought diligently over the last 9 months to keep as many people safe as possible. And at the start of the pandemic, every Thursday night, the whole nation almost would come to a standstill, and we would go out on the streets outside our houses and we would clap to show our appreciation for the National Health Service. And it's not just been the National Health Service. There have been a huge number of sources of inspiration. We have had teachers working diligently to keep our schools open. We have had people working to keep our essential services open and to keep us safe as possible. And there has been in the UK, and not just in the UK, but around the globe, a great coming together of people in solidarity to work for the success of overcoming COVID-19. But tragically, it has been unbelievable as well in terms of the devastation. There is a picture of an inside of a cathedral where you have coffins lined up waiting for burial. In the UK, we're heading towards 60,000 people have lost their life because of COVID-19. It has been pretty devastating. But pain teaches you more than pleasure, failure teaches you more than success, and poverty teaches you more than prosperity. Adversity teaches you more than comfort. That is a quotation from someone who is well known for thoughtful and reflective writings about situations. Now, COVID-19 has had a big impact on everybody, and what I would like to do is, in a sense, give a personal reflection. I live in the United Kingdom. You know that the United Kingdom consists of 4 countries. It consists of England, it consists of Scotland, it consists of Northern Ireland, and it consists of Wales, and I live in Wales. And on that map, I live in A and I work in B. And 5 days a week up until the middle of March, 5 days a week I would travel from A to B. If we blow that up on the map, you can see that it's a reasonable distance. It's about 40 odd miles by the time you negotiate some of the roundabouts and everything else. And typically on an average morning, it can take about an hour to get to work. And sometimes on a bad day, if there's lots of traffic, it can take an hour and a half. Similarly, coming home, it can take an hour, hour and a half. For the last 38 weeks, since we've been in the situation we are because of COVID, I've not made that journey once. We've been working at home for the last 38 weeks. Now, that has meant for me a huge saving, really, in terms of my salary. A big portion of my salary is paid out every week in travelling from the place I live to the place that I work. Fuel in the UK is pretty expensive per gallon, and I would estimate that with the wear and tear of my car, the fuel I've saved, you work the calculations out, 38 weeks I've not been to work, you multiply that by 5, you multiply that by 8, you get into a considerable sum of money being saved. Now, COVID-19 has changed the way that we think about work in the UK, and reading what I've read about the rest of the world, it's had an impact on the way people consider work in the rest of the world too. We've realised that we can do a lot online, we can do a lot remotely that we didn't think possible previously. Now, going forward, if I could reduce my going to the office by just 2 days a week, maybe I could reduce it by 3 days a week. But going forward, if I was to reduce my going to the office by 2 days a week, typically we work in the UK for 45 weeks of the year. Over a period of a year, going forward, I would be able to save, again, about £720, which is a significant portion of my salary. But not only have I saved money, I've saved time. If you were to work out on average that over the last 38 weeks, let's say I've saved 50 minutes going to work and 50 minutes coming home, you do the calculations again, and I would estimate that I've saved at least 35 working days by not traveling from work to home. Not only have I saved that 35 working days, but I've become a lot less stressed, because sitting in traffic jams when everything is not moving is frustrating, and can cause a lot of frustration and ulcers to grow. Working at home has not only saved time, but saved all that hassle as well. Now, again, if going forward I was to reduce going to the office from 5 days a week to 3 days a week, the number of working days I would save in an average year is 16. And again, in all probability, I could probably reduce that going to the office by significantly more. But it's not all about saving. It's estimated in the UK that the money that's been spent on COVID-19 by having to shut down lots of shops, lots of restaurants, the number of people travelling by train is reduced, on buses is reduced, and that has a cost that a lot of it has been borne by central government by borrowing money, and the estimate is that COVID has cost the UK government about £18,000 per working person. So that's not per person, it's not per capita, but for each person that is working full time in the UK, it's cost the government about £18,000. Now, if you remember back to the calculations, I've saved approximately £720 per year going forward when we get back to some kind of normality. And so even on that basis of a £720 a year saving, it would take me 25 years to make my contribution to paying off the debt that's been accrued because of COVID-19. And so not only do I have to make that saving to be able to make my contributions to what the country has paid, but when we look at what COVID-19 has done to us as a world, it has shown that we're a very small place, that we're an internet-connected place. What happens in one place really affects what happens in another. And another crisis that's coming down the road at a tremendous rate is global warming and climate change. And again, we've learned because of COVID something that we should have known before, that the world is a very small place, and what impacts one place impacts all. And I'm not the only one. This is a picture of a tube, an underground railway in the UK. And the hassle that I have in going to work is multiplied hundreds and thousands and millions of times up and down the land. And it's not just in the UK, it's around the globe. There is a big issue that we travel more than we might need to. And travel very often is uncomfortable. This is, as I said, an underground railway station where people are trying to get on the train. And in the mornings, it is chaotic. People are trying to push on and get into a space that really isn't a space for an individual, but they push on, and when they've pushed on, we'll push on. And it is a crowded, it's cramped, and it's an uncomfortable environment. Now, COVID-19 has changed the way that we work, the way that we do things, but one of the things that I've noticed is that it's impacted the way that we do things in terms of our health systems. As I said, a lot of my research is linked to the health systems within the UK. And what has happened over the last 9 months is that there has been a rapid change in the way that we access the health services within the UK. The man in the United Kingdom that looks after our health service, who has oversight, is the health minister, whose name is Matt Hancock. And he has said that by default, he hopes that in future going forward, that all GP consultation, that is all consultations with your local doctor, the doctor that is the general practitioner, the one that sort of acts as the triage between you and hospital facilities, that all GP consultations should be remote. That is, they should be online. Now, the Royal College of GPs has expressed concern, saying that it would oppose predominantly online systems because they argue about face-to-face contact being very important to be able to ascertain what is going wrong with someone. But the reality is, over the last 9 months, people's attitudes have changed. People have become far more relaxed about engaging with various people, including medical profession, online. It's a bit of a personal tale about how COVID-19 has impacted things. That man sitting next to me is my dad, my father. He is 87 and he looks quite healthy, but the reality is he has a number of significant conditions. He is in remission, but he's had cancer previously. He has had a number of problems with his heart. He has heart failure. And even though in the UK we have a very good medical system, sometimes it's very difficult to see the people that you need to see. In August, my father had a lump on his head. And usually what would have been the process in the UK is that we would have made an appointment for him to go and see his general practitioner. The general practitioner would have examined his head and would have concluded that what was on his head shouldn't be on his head and that it needed to be removed. The general practitioner would have referred my father to a consultant who specialises in the kind of lump that my father had on his head. We'd have had an appointment with the consultant. The consultant would have confirmed what the GP thought, that the lump shouldn't have been there and needed to be removed. We'd have had another appointment to go and see the consultant again in a hospital setting where the growth would have been removed. Because of COVID-19, there is a massive drive to reduce the number of interactions one-on-one with medical professions. And so what happened is that we were asked to send the GP a picture taken with a mobile phone of my father's head. The GP had a look at it and forwarded the image to the consultant. The consultant looked at the image and then had his secretary contact my father to go and visit the hospital at 3 o'clock on a particular afternoon. We arrived at 3 o'clock. My father went into the room with the consultant. The consultant was already prepared. He removed that growth and we were on our way home from the hospital 15 minutes after getting there. The whole process had been reduced in time, in expense, and had become massively more efficient. COVID changed for the better the way that we interact medically. Something else that has changed phenomenally. I went to work on a Monday morning. I taught my classes as normal on the Monday. On that Monday night, the government announced that because of COVID-19, things had to shut. And with almost no notice, just a few hours notice, we moved as a university, not just us as a university, but universities across the country, schools, everything moved very rapidly online. And it was disruptive. It was a big shock to the system. And there was a very steep learning curve. But very rapidly, we adapted. Our students adapted. The processes adapted. The way that we did things adapted. One of my friends, Tom Crick, is a co-author of a paper that talks about COVID-19 and the digital disruption in the UK universities, afflictions and affordances of emergency online migration. Going from a process of being in the classroom, teaching traditionally, moving online overnight, a very quick turnaround, something that without COVID would have taken years to change and impact, had to happen overnight. Other things that have changed for me because of COVID. Before COVID, I'd never heard of Zoom. Now a lot of my interactions with people are via Zoom. Before lockdown, I would regularly travel to Cardiff, London and elsewhere for very short meetings. I would spend far more time traveling than actually in meetings. My research students have become far more proficient at online collaboration. The companies and businesses with which I work have become used to online collaboration. My colleague is going to talk in a little bit about a project that we're working on with a company. I first started working with Robert at the very beginning of the year. When he started working with us the first week of January. We met several times, almost every day really, in January. And for the last 38 weeks, we haven't met in person. Before COVID, up until COVID struck, we used to meet with the company regularly in person for meetings, for discussions. Since COVID, for the last 38 weeks, all those meetings have taken place online. And so the companies, the businesses with which we work have become more used to working online, and it's become a big change factor, really. Before, people traditionally would have to move when they had a job in a different place. Now, working with the same company that Joe works with and I work with, we have someone that's working in India, we have someone that's working in the north of England, and the geography of actually the place of working doesn't matter so much anymore. I've done my first PhD viva using Microsoft Teams. I have acted as an external examiner in Singapore without flying there. Things that at the beginning of the year, just 9 months ago, would have been not allowed. For many, COVID-19 has made the world a much smaller, a much more interconnected place, more of a global village. But it's also highlighted that there are big differences. In our schools in the UK, there has been a big problem with children not being able to have connectivity to the internet. There's been a big problem with people that haven't got connectivity to the internet being able to access medical resources. There has been a big issue with some of our students at university not being able to access the materials that they need. And going forward, I would suggest that one of the big learnings that governments need to make, and universities and schools and colleges and everything else need to make, is that connectivity via the internet is probably as important, if not more important, than connectivity via our roads. In the UK, as in common with many places in the world, there is a problem with traffic congestion. We build bigger roads and bigger roads and bigger roads, and as soon as they're built, they're full. The capacity for filling them up seems to be endless almost. And yet, what do we need to do going forward? Well, I think if we had more bandwidth rather than road width, allowing people to work far more connected from home, then things would be a lot better in terms of lifestyle and in terms of impact on the environment. COVID-19 has taught that adversity, there can be many opportunities. It's a learning experience about how to do things differently. In the UK, it is estimated that 60% want to stay at home, working at home after COVID. They've learned to adapt and to work effectively from home. Working from home is not without its challenges. Working in the same place as you live the rest of your life can be challenging, but it can also have a significant beneficial impact on the way that we live. It can help us grow back greener in a more sustainable way. It's also highlighted that we need to have reliable data. If we're to have an interconnected world, then that interconnected world needs to be driven and reliant on data. One of the things that caused one of the most chaotic things in the UK was when all the exams in school were cancelled in June. And people, the decision was made that instead of students doing exams, there would be a prediction based on a number of factors about what marks students should get. And data was applied to various algorithms, and unfortunately, the algorithms skewed the results in a way that was disadvantaging people from certain backgrounds. And so, after a lot of heartache and a lot of soul searching, all the results had to be recalculated again. And as we move into a new world that is more interconnected, a world that is more data driven, then we need to make sure that the data we use and the algorithms that we use are effective and fit for purpose. And again, that is linked to some of the research that I'm involved in. COVID-19 has given new opportunities. It has shortened the timeline from idea to implementation. We've talked already about moving online very rapidly. We've seen the interventions in terms of medicine improving rapidly over the last 9 months. We've seen even vaccines that would have normally been 10 years going from idea, conception to production and delivery, being delivered in less than 10 months. It has made research and innovation even more important. It has been a wake-up call about other impending issues, such as global warming. COVID-19 has changed things. Stephen Hawking's a professor that's died a few years ago in the UK. One of his quotations was that intelligence is the ability to adapt to change. Thinking of another previous science, this Charles Darwin, he said that it is not the strongest in society or the species that survive, nor is it the most intelligent that survive. It is the one that is the most adaptable to change. COVID-19 has changed things. One of the things that we need to ask ourselves as individuals and as researchers and as research groups and as society is, how has it changed us? Thanks for listening. It's been a privilege to speak. It's quite difficult to know who's listening and who isn't as it's broadcast on a webinar. But wherever you're listening, I hope that one day that we'll be able to meet and to communicate in person. So thank you.
Thank you, Dr. Andrew. We were listening to you, and the audience on Facebook is also listening to you and watching on the Facebook. We have already shared the link in a chat box. If someone is facing difficulty over here, he can view the video on a Facebook as well. So we have been working with Dr. Andrew from last 5 years, and we have a number of publications with in collaborative work, and we are working on few right now as well. So in this context, so we would like to have work with the Dr. Robert as well. So I would like to ask Dr. Andrew Weir to introduce Dr. Robert Bishop for a talk.
Hi, it's my privilege to introduce Dr. Robert Bishop. It's a bit confusing because he goes by the name Joe, and that sometimes causes people confusion. But it's been my privilege to work with Joe or Robert for the last 10 months. As I said, it's been quite strange working together because we were meant to have an office next door to each other, and that did happen for a time. But for the last 9 months, neither of us have been to the university campus. We work with a company that is a very innovative AI-based company, in particular providing services to the construction industry. Joe's background is in mathematics, but he has a lot of AI and programming experience as well. He did his BSc and his PhD from Cardiff University before joining us at the University of South Wales. Joe also is a fluent Welsh speaker. His first language is Welsh, but he's also very good at speaking in English, so I'm sure you'll understand him. So over to you, Joe.
So thank you, Andrew. Thank you. You're too kind for that introduction. I'd like again to thank the organisers for giving me this opportunity to speak and give me this platform to present my work. So as Andrew said, I work with Andrew. We're from the University of South Wales in the United Kingdom. I'm a researcher there, that's my job role. And my project is to try and improve health and safety on construction sites. In this talk, we'll focus on construction sites in the United Kingdom. Obviously, this can be applied worldwide, and hopefully in future it will. So in the United Kingdom, there's around 1 death on a construction site every single week. And then additionally, there's over 150,000 accidents, a lot of which we believe are preventable. So the way we're going to try and prevent accidents is look at 2 different types of health and safety forms. The first form we have is called the risk assessment. The risk assessment is a document that's in a very table-like structure. It's in columns, everything is in its nice order. I'll show you an example later. The method statement is a little bit more tricky. It's a document of about 20 pages long, free-flowing text. To extract information out of this will be a lot more difficult, but again, I'll show you examples later. So as promised, here is a standard risk assessment. Not all these risk assessments look exactly the same, which is one reason we have, one difficulty we have for extracting data. But here is a typical example. So as you can see on our first column, it's activity. And these are activities that one person might carry out on a construction site. So just for the first, as an example, lifting into position of overhead gantry crane, which is an activity that one would expect to carry out on a construction site. However, there's a risk with putting loads on cranes, is the load can fall off. And if we look into the control measures column, these are preventions. So there's 2 different ways we can prevent accidents from happening. We can try to reduce the likelihood of the accident happening, or we can try to reduce the severity. So in this case, on a construction site, if they're using a crane to lift up a large object, the operator will blow an air horn, and the air horn will signal all the workers on the ground to leave the path where the crane is. So it's impossible then for any load to come loose and land on the person, often causing lots of damage. The second hood, another way they can reduce the risk is to obviously make sure the load is attached correctly. Sometimes with workers, sometimes with companies, they'll have instructions that one person must check it's attached correctly, another person must double check that person. So I'll again try to reduce the risk of loads falling off. Because obviously not only we have problems with humans, obviously humans getting injured and hurt, but also cargo falling off cranes can be very expensive to replace, and also it could slow down the construction industry, which again is a financial implication. So an example of reducing the severity, so we look at our second example here. So if you're trying to cut pipework to the correct size, again, an activity very commonly done on construction sites, we'll have the risk is flying debris. So sometimes when you're cutting pipes, bits of metal can strike the person cutting. So one way we can reduce this is use PPE, which is personal protective equipment. These are items such as gloves, face masks, goggles. And the idea of this control measure is instead of the debris will still hit you, but if you're wearing this protective equipment, it will cause less damage. So one thing to note is if we take just the first row, we have one activity, which is lifting into position of overhead gantry crane, which is linked to one risk. And this one risk is linked to two separate mitigations. So there's two different mitigations from one risk. So it's not a one-to-one-to-one relationship. It could be one to many to many. So we call an activity linked with a risk linked with one control measure. We call this a triple, generally because there's three of them. So as I mentioned before, a method statement is a large document, usually around 20 pages long. And this includes lots and lots of information. So some information like where is the nearest hospital, who's the supervisor, who's in charge of doing what. But the part we're interested in is this part called a sequence of work. And what happens is this is a document, free-flowing, full English text that will say what is done in which order. So we have a goal here. How can we make construction sites safer? Well, three things come to mind. We can try and improve these documents. And what I mean by that is, say if we have an activity and the user writes a risk, but may miss a mitigation. So we could try and suggest improvements by filling in, these mitigations. Also, they might write an activity and forget to write the risk to do with that activity. So again, we could suggest this as, sorry, you may have missed this risk, and hopefully this will reduce accidents and save lives. Another issue that we have is, can we compare these two documents? Occasionally, these documents are written by two separate people. So sometimes one document might miss information that the other has. So if we can find a way to compare these documents, we can try and use that to bring this to their attention and hopefully reduce risks this way. There's also a third type of document. It's quite unfortunate this one exists. When on a construction site an accident will happen, the company will write something called a safety briefing. And what the safety briefing is, it's a document that tells you what happened. So how did this accident happen? Why it happened? Is there faulty equipment? Was the operator not using the equipment correctly? And most importantly, how we can prevent this happening in the future. So the idea of this is, given a risk assessment and a method statement, we'd be able to suggest safety briefings. The current issue with safety briefings is that you could have an accident that happened 6 months ago, 2 years ago, 5 years ago. It still could be likely to happen. However, you could have people may have just simply forgot about the previous incidents, or if you have new staff and they might not have been aware of the incidents in the first place. But the impracticality comes is you can't expect a worker to search through every single safety briefing to see if it's relevant or not. So hopefully we can try and use AI, natural language machine learning, to automate this process. So the first point I made was, how could we suggest improvements? Well, the nice thing about the risk assessment, because it's in tabled format, the data is almost classified for us. So what do I mean by this? So in the first column, we had activities. In the next column, we had risks. Then a few columns later, we had mitigations. So we know that the first column, every element in there is an activity. The second, every element in there is a risk, etc. So everything is pre-labeled for us. Also, because of the way the rows are structured, we know that the first activity corresponds to the first risk, corresponds to the first mitigations or control measures. Yeah. So as I said here, we have our first activity, which produces one risk, which produces one control measure. So this is what we call a triple. So what we do, we have a part of our, we built a software which we call the extractor, and we input thousands of these risk assessments, and it will try to detect the table, try to retrieve the activity with its corresponding risk and with all the corresponding mitigations, and save these into a database as follows. So our database looks something similar to this, obviously a lot larger. And I mentioned before that sometimes, so what the idea of the software is to use is that someone could show us a risk assessment, and we hopefully will be able to say, yes, there's sensible improvements we can suggest, or no, there are not. So if we have the risk, so someone sends a risk assessment with the triple in it, falling into a trench, and the risk being drowning in a waterlogged trench, which is a very common problem we have, especially in this country. It rains a lot, and people forget that if you dig especially large holes, people can fall in and drown, which is how, unfortunately, a few accidents have happened over the years. So we've got two mitigations for this. So we can check holes or trenches are not flooded, and if they are, we can use pumps to physically remove the water. However, in our database, we have something that's fairly similar. So if we compare the activities are similar. We compare the risks. We see the risk is similar. However, if we compare the mitigations, they're different. Because one is talking about checking holes, and the second in the database is physically adding a barrier to prevent people falling in. So what we could do is we could suggest this triple to the user and say, look, why don't we could suggest them, hey, you could erect barriers around holes and this prevent people falling in and unfortunately drowning. Similarly, we've got to be careful because obviously we don't want to send too many suggestions or too many useless suggestions to the user. So if they have something similar, again, their risk is changed to use measures to protect the edges of our trench. And the closest thing in our database is the previous triple. So we can see that the activities are similar, the risks are similar, and also the mitigations. So this is a triple that we should not suggest because it's already included in the document. So I kind of skipped over how do we get the closest match in some sense. Well, obviously natural language, computers can't read per se. This is it's an open problem, but there has been efforts to close it. So what we do is we use this idea called Elasticsearch. So Elasticsearch is a function that looks like this. Yes, quite scary and intimidating. However, these are what the terms will say. However, I believe that the elegance of this search function relies on two terms: the TF, which is term frequency, and the IDF, which is inverse document frequency. So a remarkable thing about term frequency and inverse document frequency. So it was kind of brought about in the 70s, 1970s, and still today, I believe a survey in 2015 stated that around 80% of text-based searches still have IDF, term frequency, inverse document frequency as a part of them. Which, considering the speed of how technology and computers evolves rapidly, and an algorithm or an idea from 30, 40, 50 years ago still holds. So term frequency is the number of times a term appears in a document. So if you have in these, let's say, a safety briefing or a risk assessment method statement, how many times does every single word appear in that document? Okay. And I believe where the magic happens is the inverse document frequency part. And what this is a measure of how rare a word is. So if I was to pick up just a random article, and I've seen words in it like digger, crane, spade, worker, without really knowing the context of the article, I would assume that this article has something to do with construction. And the reason that would be is because the words like crane, worker, digger would appear a lot in that document. However, if I was talking about a different topic like sport, we would not expect to see words like crane, digger, worker appear infrequently, if at all. So one thing about how humans interpret things. So if we just read this single triple, we see words like burying, trench, and hole. But automatically as humans, we understand that this triple has something to do with digging or excavating, even though that nowhere in this triple the words digging appears. Similarly, in this method statement matches the previous risk assessment. We have words like excavation, permits to dig, so cat is a type of digger. So we see that this document is also to do with excavation. So the idea is can we link these documents? Right. So again, a problem that, again, it's not fully closed in machine learning, neural nets, natural language, is the problem of comparing two sentences. So what we could do, if we can compare two sentences well, then we'd be able to find out, is there missing information between the risk assessment as the method statement? So has one person wrote something about the method statement which is not present in the risk assessment? So obviously, if it's not present, then this could cause risks later. This could increase the probability of risks further down the line. Another use of this would be to compare risk assessments and method statements to the safety briefings I was speaking about earlier. So instead of a worker looking for reams, files and files and files of these safety documents, we could intelligently suggest, look at these. And again, hopefully then this would reduce risks. So questions to ask. Well, what makes a word important to a document? And I kind of touched on this before with term frequency and burst document frequency. As in, if a word appears a lot in a certain document and it's rare in a corpus, then chances are it's unimportant. Another issue we have is, how do we convert words into something a computer uses? I mean, a computer uses binary, ones and zeros. However, how can we convert words into numbers? And this, probably the most important part is, how can we know that two words, sentences, or documents are similar or not? So if I said the words like hammer and nail, we could say, yes, these words are similar to some extent. However, if I said a word like football and hammer, well, these words are not very related at all. But how we know that as humans by intuition, but how does a computer do it? So the most basic method that someone can vectorize words is called one-hot encoding. And what we do is we replace words with a standard basis vector. So what a standard basis vector is, it has zeros everywhere except for one position where it has the number 1. So if I said the sentence, the man could easily use the spade because it was light. Well, we can encode that. So what we say is we take all the set of all unique words. So there's 10, I believe. So for the first word, the, we have a 1 in the first position. For the second word, man, we have a 1 in the second position. So if you notice, the word the appears twice. So it has a 1 in the first position again. So it's the same, it looks the same as the previous vector. So some immediate drawbacks we have to this sort of method is it has the same representation. Well, it might be okay for a word like the, but however, the word light has 2 different meanings. So this sentence could have meant that the spade was light, which means it was easy for him to dig with. However, it could have been talking about it was light outside, as in it was not dark, he could see, which made his job to dig easier. So this sentence is ambiguous. However, the computer using one-hot encoding would interpret this in the same way. But however, given the disadvantages, there still are advantages. We are able to create a vector space, but as I said further on, it doesn't take semantics into account. So what semantics are? So if I said, if I put the word not, so the man did not dig the hole, or the man dug the hole, they would be similar, even though one is the total opposite of the other. Also punctuation. The classic sentence we have in English is "Let's eat grandma." The comma there can be very important. Every unique word is the same distance apart. Well, this is not what we want, because we want words like hammer and nail to be similar. And however, we want words like book and nail to be very far apart. But this doesn't take that into account. Also, in English, we have words the same spelling with two completely different meanings. And again, this doesn't take into account. So what we would like to be able to do is create a vector space. I've just shown a two-dimensional representation. So generally, when you have a vector space, it will be in, a vector space could be, you're looking at a few thousand dimensions, up to about 20,000 dimensions. In the English language, we commonly use about 20,000 different words. Obviously, we try and reduce that as much as possible. So here, if we see, we put some 4 words on our graph. We have cat, dog, nail, and hammer. We see that cat and dog are similar to each other. And we also see hammer and nail are similar to each other. However, cat and nail are far apart, same with cat, hammer, etc. So if we could build a vector space that has these properties, then we'd be able to understand the English language go better to work with. So if we're talking about graphs and talking about distances, we have to mention a metric. And what a metric is essentially a measure of how far 2 points are apart. So this is the most standard metric, the cosine distance. Essentially what cosine distance is, you can have this with the inverse cos by all means, but the cosine distance is essentially the angle between two vectors, and the idea is the smaller the angle, the more similar they are. We can use the Jacquard distance, and again, this is a measure of closeness. So in like one hot encoding, the intersection is how many similar words they have, and over the total. And here we have the Euclidean distance. The standard way we would measure something is in from point A to point B with a straight line. So those in maths, we call this the altitude norm, which should be normalized. So there are some pre-trained vector spaces out there. So two most common, in my opinion, are word2vec and glove. So one of the advantages of pre-trained models is all the heavy computing has been done for you. So that's, so if you could, if you don't have a powerful enough computer, you couldn't build the models yourself. However, you can still use them. And the second thing is they're very easy to fine tune. So with myself, I'm using jargon or words specific to the construction sector. So I can easily give it more information about the construction sector, and hopefully it'll be able to improve a lot more on these specific words I'm interested about. So this is using the standard word2vec model, and basically I'm asking how similar are these words. So the first we have dig to spade, and we see 0.35 score. Sorry, so 0 is the lowest, as in they've got nothing in common. 1 is the highest. Everything's been normalized. So as we see that dig and spade, not that similar in this case. Again, electrician and plumber, fairly similar, and boy and girl, very similar. But if I pre-train my model, so I feed it information about the construction sector, then what we see is dig and spade, the similarity increases as we would expect. Something kind of unique, electrician and plumber decreases. I believe this is because when you're dealing with these construction activities, they're essentially separated out into different activities. So like a plumber and electrician generally come in separate documents rather than together. And again, boy and girl has stayed the same. So quickly before introducing BERT, we've got to speak about what a neural net is. So a recurrent neural network is essentially we input words from a sentence one by one. And the idea is the first word you input, parts of that will go to the second word. So as in the English language, when we speak, the context of the word usually relates on what's said before or after. So it's using other words in that sentence to give extra meaning to the word, to the current word. So one of the main drawbacks, well, two main drawbacks of this method is as we pass down through the model, the weight of the first word almost diminishes every single time. and it only reads right to left. In some contexts, you'd like it to read, sorry, you can make this model read right to left or left to right. It doesn't really work both ways. But sometimes in a sentence, you would like your context from the word after rather than before. So the problem has been solved with the first word vanishing. So what we have this thing called long-term, short-term memory, and they have these things called forget gates, which essentially is the memory of the system, and it controls how much of. So it controls if the first word is important enough to carry on, or it controls the weighting of that. But the main tool I use is BERT. BERT is a brainchild by Google. It stands for Bidirectional Encoder Representations from Transformers, which is a mouthful, which is why BERT is a very nice thing to say. So apparently, BERT was trained on around so this is 3,000 million words, or 3 American billion. It was trained and I believe as well about 250,000 novels as well. So it was trained and supervised. This is very advantageous because obviously supervised learning, you cannot label this sort of data, or it would be a very difficult task, at least to label this volume of data. So we use something called a mask language model. So what that essentially is it sort of hides words in a sentence and see if it can repredict what was hidden. So it tries to guess what word comes next or what word could make sense possibly. It also has like a next sentence prediction. So given a first sentence, what would be a sensible suggestion for the next sentence? One quite amazing thing about BERT is it uses context. It can use context. So we could use the previous sentence as the input to the current sentence. So hopefully you give context that way. The main advantages of Google, it reads both right to left and left to right. So as before, if the context comes before or after, it should reduce that effect. It's very easy to fine tune. So with me, I want to make mine very specific about the construction sector, so I can fine tune it to the construction sector jargon. It's pre-trained. So one of the main issues, if I was personally to try and train a model of this size, again, I'd have to use an awful lot of computing power. So not only would this cost time, and obviously you must be able to have access to the equipment in the first place. Again, very expensive in the energy costs as well. So it's kind of nice that someone has pre-trained one model and everybody can use them. So the main disadvantage, not necessarily about BERT, but about machine learning in general, it's a black box. We don't really understand what's happening. So some results I've got. So I've used the standard BERT model to give me the similarity between two sentences. So as you can see, our first sentence is digging a hole, and the second sentence is digging a trench. And that score with an untrained BERT model is about 0.73. Fairly similar, which is what you'd expect. However, for the second sentence was slipping or tripping into a hole, and the next sentence falling into a trench. I had quite a low score in my opinion. Personally, I would say that these sentences are more similar than that. And again, similar story with the last sentence. So what I've done is I pre-trained my BERT model and with the construction sector jargon. And what we found is we had an increase in the comparison between digging a hole and digging a trench. It's kind of a small increase, but considering it was quite accurate to start with, it's what I would expect. However, if we look at slipping or tripping into the hole and falling into a trench, this has had a massive improvement. It's something I would say is a lot more acceptable. And using preventative measures to protect the edges of the trench, and you compare that to erect barriers around the hole. I don't think I've trained it with enough data for it to make these sort of connections, because these, in my opinion, the score should be a lot higher. So what we also done was, before BERT, we used a bag of words approach. So you have all the words in the sentence, you put them into a bag, and basically you see what's similar or not. And we combine this with Thesaurus, or a Thesaurus that's been pre-written by the startup company I was working with. And the idea of the thesaurus, it was tailor-made to construction jargon. So here we have trench and hole be the difference, but the thesaurus corrects that. So again, we have a perfect match here, but we see the results are a bit worse for the second two. So this is the difference between a pre-trained natural language model versus something that doesn't rely so much on machine learning. And thank you. That's the end of my talk.
Thank you, Doctor, for this informative talk. We will actually get the question in the end, but right now, one of the participants actually posted that if we are using some contraction instead of two words, didn't it cause an error? So that was the question from one of the participants, that is Saad Ahmed.
So if you would like, it depends. You can treat this how you like. So one common method is if you have a contraction like it is and it goes to it's, you can just remove the apostrophe, the contraction altogether. So the word is ITS. That is one way you can get around it, or another way is you could replace the apostrophe or the hyphen with just a space. It depends on use, but yes, it is something that gives problems, or you could make your own dictionary and replace the contractions with the separated out words. That's also possible to do. But yes, it is a sticking point.
Dr. Wajahat has some questions. So, Dr. Wajahat, if you want to ask.
I just want to ask a simple, like, when we are using BERT model and there is one more Roberta model, so how, or the NMT. So in your opinion, which is the more, effective one as compared to NMT? Yeah.
I personally am a fan of BERT. It's the one I'm more familiar with, so I suppose my answer is kind of biased.
Okay, fine. Perfect. Yeah.
Dr. Robert. So I would like Mr. Ali Izaz to introduce our next speaker.
Thank you very much, Tanveer and Dr. Robert. It was a very informative webinar presentation from your side. Now I would like to introduce Dr. Wajahat M. Qazi. He's assistant professor and in charge of intelligent machines and robotics, Department of Computer Sciences in ComSets University, Lahore. He's also founder and co-founder of many startups. Prominent out of them are Nikog and QuickBee. Whereas he has a vast profile, he has been associated with IEEE, and he has been working for NDC, Ministry of Defense. And Doc Saab is also, Doc Saab, I've also heard a lot from Mr. Tamim Fari. So I would wholeheartedly invite for you to listen to your talk very anticipatingly. Thank you.
Yeah. Thank you, Ali. Thank you, Hamza, and everybody. Assalamu alaikum. This is Wajahat from ComSets Lahore campus. I hope you can hear me loud and clear. So today what we'll be discussing, it's more like an introduction to quantum computing for those guys who are like, want to have some basic idea that what really is quantum computing all about. And definitely quantum computing is like the future of computing era. And at the same time, it's a new computer science. So in order to understand what are the basics of quantum computing, like I would just simply like to request my audience that just simply forget about whatever you know about the computers, because none of those computing concepts are going to be applied today as we speak about quantum computing. Just for the sake of a little flavor of this statement, that when we talk about information or data in computer sciences, it's more like we are talking about something which is logical in nature. But when it comes to quantum computer sciences or quantum computing, the information is no more logical; it's physical. You see, the fundamental construct on which we have been, working on, the entire nature of that construct is changed. So when that nature is no more the same, then it means that the entire computing paradigm is no more the same one. So in order to understand the functioning and the working of these quantum computing or quantum computers, just simply just unlearn what you have learned, and then start writing new concepts over here. So let's try to build some basic, idea over here that what are we going to deal with in quantum computing. So there are two basic observations in our life. As you can see in our picture, that in figure B, if we are throwing some balls, and there is a barrier over here, and there are two holes, like we have maybe a hole A over here, maybe, and this is our hole B over here. So it means that either these particles will move from hole A, hole B, or they will bounce back. So there is no possibility that the same ball actually passes through both holes A and B at the same time. That is not possible. So this is a common observation which we see in our real life. And there's another observation when we talk about waves. So, like if you're standing at the bank of a pool and you are like observing the water waves, how they are moving, and you perform the same experiment, you will see that water waves will be, having such behavior that these waves will be intercepting with each other, and the point where they are intercepting, the energy level will be high as compared to the other part of the waves. As they touches the wall of the pool, after some period of time, you will see that there is some kind of rusty spectrum over there. So these are two common observations which we see in our daily life. So this is what is the classical view of the things which we experience on our day-to-day basis. Now, what happens when we go into the quantum world? So before touching this quantum world, if someone is not familiar with this quantum world over here, it means that we're talking about atoms and subatomic particles like electrons, protons, nucleus, neutrons, quarks, and unified field. So all those, inner world down the abstraction of that atomic layer. So when we go into that world, so now assuming this thing, that what happens in that world. So if somehow we are able to extract electrons from those atoms and we try to perform the same experiment, so what will happen is this, that electrons are more like the particle-like objects, like balls, small balls. And when they are moving, okay, fine, a ball can move from A, from B, as we have discussed. But the interesting part is that we won't be observing this kind of behavior on the wall. Rather, we'll be experiencing wave-like behavior on the wall. No, this is really amazing. That electron was like a particle, or any atom, or whatever you are using as a substrate in this experiment. If it is an atomic or subatomic particle, we will be observing some spectrum, some wave-like behavior. Now, how it is possible? So this is the very fundamental concept over here, which is going to be the building block of quantum computing. So as mathematically, this is really interesting. Mathematically, it means that one way or the other way, a particular particle was at the two places in same time. And that is something which is not, acceptable for a common mind. So what scientists or the physicists that did is that they started putting detectors over here to observe that when a particle is crossing this barrier or this slit over here, are they having a wave nature or are they having the particle nature? So the interesting part was this, that when the detector was placed over there, so the observation over here was like a particle one instead of a wave-like structure. So this is another interesting behavior, then that when we place a detector, the particles are behaving like a particle. When you remove the detector, it means that your particles are behaving like a wave. So from here, the concept was formulated that subatomic particles have dual nature. So they are particle and they have wave. They are both at the same time. So this is something which brings us with two very important concepts in quantum mechanics, which is the fundamental, science of philosophy for building quantum computing and quantum computers. So this very nature of these quantum particles having dual nature or the dualistic, behavior brings us to a very important concept, which is called superposition. So what really is superposition? Something like this. This is the animation, which is simply saying that a quantum particle is a particle and is a wave at the same time. So if like over here, it's a wave and it's a particle, both things at the same time. This is superposition. Now, what really happened is this, that coming back to the point, coming back to that basic assumption that a particle is in two places at the same time, it means that that such existence means that these two counterparts of the same particle are entangled with each other. So this gives us to another concept about entanglement, which means in the universe, regardless of their position in the universe, two components or two particles are entangled with each other. If one particle is representing information state 1, then it means the other one will be representing information state 0. So this is really interesting, that if I toggle this one, which is 1, for instance, then it's assumed that two entangled particles cannot have same state. So according to the law of quantum physics, the other one has to flip to 1. So it means that it's a true parallel processing over here, because we won't be needing iterative processors or loops to go one by one into our a collection of values and try to perform all those computation, because all of these configurations are entangled with each other. Just imagine this thing, that you have one atom or one electron which is representing a 1. So it means that the counterpart of that one which is entangled is representing 0. So if I want to calculate the NOT function on this particular bit or this particular information, so what I'm going to do is that in one round, in one cycle, I'll be computing both things, because all of these values are entangled with each other. So this is really exciting, a very different concept which is not really present in classical computers. Second concept is another one which is really interesting, when we talk about that in quantum computers we don't have information loss. So there is no information loss over here. So what do we mean by information loss? If matter speaking, like if we simply experience that you have an AND gate. You might have observed that in case of AND gate, what we have this thing that for example, if you have two inputs and one output, if you are giving 1 over here, 0 over here, so you're getting logically 0 at the end. So what does this physically means? That you have 5 volts over here, you have approximately 3.5 volts over here, and at the end you are getting 3.5 volts over here. So the question comes where this particular 5 volt is going. So this 5 volt is basically the information loss which produce heat according to that law of energy. So it means that we are wasting a particular kind part of information in terms of heat production. So this is information loss we're talking about. So when it comes to quantum computing, we do not suffer these kind of losses, because we don't have AND gate, we don't have NOT gate, we don't have all those logical gates, digital logic gates, because in quantum computing we have quantum logic gates, which the idea of these quantum logic gates is something like this, that if you have a true number of input lines in a particular quantum logic gate, you'll be having 2 output lines. If you are having 3 input lines, then it means that you'll be having 3 output lines. So as the number of input lines are equal to the number of output lines, so which means there is no loss of information over there. So this gives us another interesting concept in quantum computing, which we call reversible computing. Well, in classical computers, apart from NOT gate, all kind of computations are not reversible. So what do we mean by reversible computing? Like if I have a function which is taking x as an input, and you get y as your output. So what do we mean by reversible computing is this, that if we put this y back into this function, then we are expecting that x will be the output. So if you ask a question, you get an answer. Then when you put the answer back into the function, we are expecting to have the question, but what was the query? So this is like a reversible computing. So as you can see that in these classical computing, we don't have this this kind of computation which is reversible computability. So in quantum computers, reversible computing is like a day-to-day process over there. So as we are representing information not as a value, in my statement, I never said this thing that a particular atom was representing one as a value. What I referred that there's a state of that particular physical particle which we are referring to as one. For example, like when the electrons are moving, so they're actually moving in terms of spin. So they have half spin. The electron have a half spin, like clockwise, anti-clockwise, clockwise, and anti-clockwise, something like this. So if we assume that this kind of spin is 1 and this is 0, so it means that when the electron is moving, that it means that it is having state 1. When it is moving like this, it is having state 0. So with clockwise and anti-clockwise, representations, we can label them like 1 and 0. So it's the state of that physical particle which we are referring to as 1 or 0. So it means the information is physical over here because they are the states rather than the value of contains in some kind of memory buffer. So there is no value and there is no memory buffer, rather they are the states of those fundamental particles. So this brings us to another very, very important concept. Okay, if information is physical, then can we copy paste those information? Like copy information from here and then paste it over there. That's not possible because there is no cloning theorem. The reason is this: we cannot clone information in quantum computing because information is physical. So in order to clone the information, to move the information from one place to the other place, you need to destroy the information from the first from its source, and then you need to transmit to the target site. So there is no copy paste over here. So connecting this, the idea of that destroying information from the physical source, from the source, and then transmitting that information to the target source, this is called a quantum communication, which is commonly known as teleportation. So when we talk about teleportation, it means we are talking about a kind of telecommunication which is based on quantum mechanical and quantum computational aspects, which simply suggests that we can actually transfer information over the communication channel by destroying the information from the source and reconstructing the information on the target side. So these are the very unique features which are unique to quantum computing, which this field is offering. So as I mentioned, that quantum computing has a lot to offer, as we can see over here, like superposition, true parallel processing, no information loss, reversible computing, and so on and so forth. So the question comes how this really works, how quantum computing would do what they really do. So from this point of view, to understand all these things, the fundamental algorithmic block over here is something different. Like in classical computers, we have computers as the substrate for computation. So in quantum computing, we have a physical system. So when we use the word physical system, it means those systems which are actually subject to the law of physics. So regardless of all those jargons in physics, the basic process in physics is the law of motion. Even when the electrons are moving, when they are vibrating, when you push some objects, the entire universe. So if you look into the physics, you will see that there is one common thing over there, that is law of motion. So it means that in quantum computing, instead of doing or regulating the computational process, we regulate motion. And as I was mentioning, that it's all about quantum particles, and every quantum particle, regardless of their abstraction, they are in some kind of vibrating phase. So it means that the motion of the law of motion is over there. So instead of computing, we try to regulate their motion. And the another advantage of this motion thing is this: like, we don't have inputs and outputs. We always have initial state and the final state, or the output state. So it means that if this is my position, right? So if I'm taking 2 steps forward, and if I reverse the magnitude of the same step size, I can go back on my initial phase, the idea of reversibility. So technically, that reversibility phenomena is also due to this law of motion regulation over here. So it means that instead of having inputs and outputs, we'll be having initial state, the output, or the final state. Instead of using computation, we'll be trying to play with the law of motion. So this is how quantum computing, the paradigm is associated with. So how we do it? So first thing is this, that we live as a human being. We are the part of this classical world, where we have either 1 or 0, or any combination of these values. But in case of quantum computers, we don't have 1 or zeros. Rather, we have states, like state 0 or state 1, something like this, which simply suggests that the quantum world is a superposition of 0 and 1. So in simple words, what really is superposition? It is a linear combination of all possible values. So it means that all possible combinations which are lying between 0 and 1 are already in this quantum world. So what we do is that from classical world, we simply give information as we deal with in zeros and ones. Once those informations are in that quantum computers, they are switched to superposition, which means that they are the representation of all possible states. And once we get the output, the final state, we collapse. I'm using a very specific word, and I'll explain what do we mean by the word collapse over here. So we collapse the quantum world and get our classical output in terms of 0 and 1, or whatever their decimal number or character representation is. So it means that we don't know. This is the real oracle, or this is the real black box over here, the quantum world. We don't know what's really happening over there, because we have all possibilities being computed at the same time. Okay, let me put it something like this: that just imagine that you have an 8-bit quantum register. So what do we mean by a 8-bit quantum register? It means that 2 to the power 8 means that we have 256 possibilities. So when I'm saying that the quantum register, 8-bit quantum register, is in the superposition, it means that in this quantum world, we have 256 possibilities at the same time. So it means the entire configuration of the quantum world contains both the question and the answer at the same time. So all I have to do, instead of computing it, I have to curate, because the answer is already over there, assuming that there is no overflow or buffer overload. So, but there is a catch also. Quantum world is very sensitive to all those cosmic radiations. So it means that this superposition collapse randomly due to the effect of those cosmic radiations. So in quantum computers, the people are trying to isolate the quantum computer, or the quantum world, or the quantum processors from those cosmic radiations, so that a random collapse may not occur. So this is one of the limitations which we are facing right now. That's why I used the word collapse before. So if everything is going as to our desire, so what really happens is that when we are running a quantum algorithm, as the quantum algorithm completes, that ends, So that quantum algorithm, after it's at the end phase, it collapsed the quantum world intentionally, so that we can get the classical information 0 or 1 or any number which is understandable by by the human beings. So whatever I've been saying till now is like a quantum bit. The mathematical representation is something like this, that that a bit over here is some kind of this representation, like over A and this B or alpha or beta over here. Beta is like the computational basis, like the probability that your quantum bit is in state 1, the probability that your quantum bit in state 0. So this is called, this is the superposition representation of a quantum bit. But the point over here is that this alpha and this beta or A or B over here belongs to the complex domain. So this is not the right time to reason that why it is in the real domain, why it is not in the real domain, rather it's in the complex domain. So the every computing over here is in the complex domain. So if you are not familiar with the word complex domain, it means that something like this, that we're not talking about simple numbers, rather we're talking about something like this, that x plus iota y. Over here, this iota is that imaginary thing, which is like the under root of -1. So states representation in your quantum computing regime, it means that the probability amplitude, which is like according to this calculation, must be equal to 1. So if your probability amplitudes are not equal to 1, it means that there is something wrong with this quantum bit representation. So mathematically, it's a matrix. A matrix in a real world domain, in the complex domain. So this is state 0 and this is state 1. So this is a matrix representation of state 0, and this is the matrix representation for state 1. And more idealistic speaking, this is alpha over here. So it means that this is going to be the alpha, which means alpha is that computational basis. So generally speaking, whenever we are trying to increase number of quantum bits in terms of quantum registers. So if we have 2 quantum bits, so their representation will be the as the tensor product of quantum bit A and quantum bit B. So that is mathematically something like this. So this is how the quantum registers are being formulated. You see, there is no Boolean algebra anymore. And so the algebra for quantum computing is your linear algebra in complex domain, in which we'll be talking about dual vectors, we'll be talking about tensor product, and so on and so forth. So just to give an idea that what kind of gates we're talking about. So as I mentioned that we don't have those classical AND gates and OR gates. So the fundamental gate over here is called C0, control not gate, something like this. We have a quantum state A, we have a quantum state B. The quantum logic table is something like this, that if we combine these two states, 0, 0, for example, so we'll get 0, 0. If we have 0, 1, we'll get 0, 1, and something like this. And this is the diagram of that notation for this C0 gate. So what really happens over here is simply like this, that if we have 1 over here, it means that this particular gate gets enabled. So whatever the input is being represented in the state B, the XOR of A and B will be the output of this one. So this is how the C0 gate is being represented. Mathematically, it's a matrix, something like this. So it means that a matrix is technically a gate over here. It's an operator over here also at the same time, because these gates are operators which are applying on operand A and B in their quantum states. So this is another gate which is really interesting one. If as I mentioned that in my preview over here, that we give inputs in terms of classical inputs, and they are translated into their quantum world. So what really happen over here is that if in your classical computers you are representing 1, so as soon as it's entering in this quantum world, this will be in its pure state, which is something like this. And as soon as it comes over here, a gate called Hadamard gate will be applied, on this state 1, which will convert this information into its superposition state. So this head-mart gate is the superposition based representation for all coming inputs. So so there's another one which is a Toffoli gate. So for instance, if someone desperately needs to apply AND operation or NAND operation or something like that, so we can use Toffoli gate, something like this, that we can fix the values of this A and B, and we can forcefully ask the Toffoli gate to act as an AND gate or NAND gate, and then we can actually perform all those activities. So this is just to give a flavor or the idea that we are using linear algebra over here. Each matrix is the representation of a quantum gate. We have number of quantum gates over here. Each gate have their own quantum logic tables. So an ordinary a normal quantum circuit is something like this, that we have a Hadamard gate, we have a Hadamard gate, this is Poly-X gate. So combination of all these gates are giving some inputs and some outputs. So this is how a quantum gate looks like, right? And the transistors are over there and capacitors are over there. So in quantum world, we don't have capacitors or transistors at a conceptual level of circuit designing. Rather, we are talking about all those quantum processes which are simply matrices over here. So when we talk about applications, that why to bother all those things? So these are some very exciting application areas where quantum computing is playing an amazing role. Like first one is the teleportation. Okay, before moving into this one, to understand taking into account all those complexities which I've shared with you, which is just an introduction to quantum computing, by the way. So why to bother? Okay, let's simply consider this thing, that I have a number. This is the example from a very popular quantum computing textbook, like 26. So it means that we have a 2-digit number. Now consider this, that I have a number with 300 digits, for example. So if let's assume this, that I have a number with 300 digits, and I want to factorize this particular problem on a computer system with 1 terahertz speed. Just imagine that how much time will be required to solve this problem. So according to this textbook example, a 1 terahertz computing machine will take approximately 150,000 years. And if we have in the right configuration of a quantum computer oscillating at 1 terahertz, that will take less than 1 second. So you can see the computing power of quantum computing. Yet, yes, we have not yet reached its quantum computing has not yet reached its full potential at this time. So we have to acknowledge, because there are so much physics and all those constraints from the law of physics are over there, which are like acting as a barrier or as a friction in the progress. But still, we have very encouraging results. Number one. Number two, keeping in view that we have this superposition thing. So it means that if we have all possibilities at the same time. Now imagine if we have an encryption of 512 bits. So if we want to crack it, what will happen? We simply ask a 512 quantum bit computer system to crack it down. So according to Boeing, I was reading one article from Boeing. So according to them, the current state of the art in quantum computing will take 15 minutes to break any kind of latest encryption models, because they already knew the answer for your questions. So that is the strength or the power of this quantum computing, which is once again the red alarm over here. So as I was saying there about teleportation or telecommunication, so China has already experimented on teleporting few quantum particles over between Beijing and Atlantic, and they have already launched approximately 1,400 quantum satellites at their 500 kilometer altitude. So this is the experiment which was done by China in 2016. So you can imagine in last 4 years what kind of progress that they have been made. So one can easily expect that maybe after 20 years or 30 years, I might be emailing a sandwich made by me through email. So Andrew will be receiving my sandwich as an attachment due to this result of quantum teleportation. So this is like the thing which we're expecting. So at this time we are able to not physically teleport objects, but rather few atomic blocks or quantum particles. Let's give some time more to the technology. As we don't have no cloning theorem, so money forgery and all those things, the next upcoming money paradigm is quantum money, quantum software protection. One of the bottleneck, as Bishop was already sharing the idea of the computing complexity which we are facing in deep learning models and all those things. So with the power of two pair processing over here and those superposition and entanglement, quantum AI is going to rebound, because now we might be having, it is like assumption over here, with all those strength of quantum computing which has to offer. Once we are there at the level of more full-scale quantum computers, we might be able to do a lot of in artificial intelligence. And this brings us to the development of quantum robots, quantum cognition. Quantum OS is already on the way. Quantum C++ has already been developed. You see, it's entirely a new playground for us to play once we are able to understand how to handle those quantum mechanics and all those these concepts. So this is like a simple picture of how a quantum processor looks like. And this is the system unit of quantum computer by D-Wave, one of the coolest place on planet Earth. What we have been doing, like for last couple of years, we have tried to develop. In my research group, we have written our own quantum simulators. We have developed a quantum cognitive architecture. So our quantum simulator can simulate 13 quantum bits on your standard laptops or PCs. And with the help of those things, we have developed an AI system which is able to dream. So I normally share this particular video in which we have a 10-second dream. So we are looking for collaborators in this field. So anybody can join us. This GitHub downlink is for our quantum computing framework, which was written in C#.NET. And by the end of this week, I'm also launching my quantum computing tutorial for beginners. This is the link. I'll be sharing my slides after this talk. You simply click this channel and you can start learning quantum computing from next week. Inshallah, thank you very much. Jazakallah. So if there are any questions or anything where I can help, please do let me know.
Dr. Saab, I have a question, if you don't mind.
Please.
First of all, this was very, informative and, very wonderful presentation. And I love that idea of, teleporting the sandwiches. Me as a foodie would be amazed and would be, in love with this thing. Sir, you talked about the two-way directional, movement of information in quantum computing. Is it similar to the control feedback system? If it is so, then what about the applications of control feedback? Would quantum computing be replacing all the control feedback applications like ABS brake, industrial control motors, and all other control feedback linked application? Number two, yes, that one is that you, said in your presentation that the information is destroyed from the receiver's sender's end, then it is sent to another end. Then that means that quantum computing would play a pivotal role in the security of information.
Yes. Okay, let me answer. Okay, well, I'll start with the question number 2 first, right?
Okay.
Yes, I totally agree with you. Okay, obviously there are always way out. When I said that in case of entanglement, if we have 1 over here and 0 over here, So these two cannot have same states over here. So there is another concept in quantum computing which is called Bell state. So in Bell state, we can have both, counterparts as 1 or both counterparts as 0. So this is a very rare state which we forcefully, put on those quantum particles, which is actually used in teleportation. Number one. Number two, yes, the idea of quantum communication or quantum encryption is like to enhance the security as well, because the entire infrastructure is black box. So when you try to steal the information from that oracle is a standard word for quantum processors. So when you will steal the information from processor, the oracle, the entire quantum computational configuration collapse. So when it collapses, it means that end of the game. You won't be having that quantum information anymore. So that could be if the collapse is wrong, it means that you might be getting false information. So it means that the oracle is or the quantum world is too much secure as compared to we witness today. And regarding your first part of the question, when we talk about feedback, so if I'm wrong, please correct me. In case of feedbacks, what we are saying that the system is generating an output, and then output is being evaluated. And that evaluation, the difference between the expected and the output is the feedback, right? So when we said reversible computing, it's not the feedback, basically. It is the actual output. So, it's not. And the second part of your first question regarding the replacement of the control system and all those things, one thing is for sure, keeping in view the complexity and all those things which quantum computing has to offer. One thing is pretty much sure that quantum computing would not be replacing our day-to-day computing. Rather, quantum computing will be the tools which will be doing all those kind of activities and helping us to solve those problems which are yet not possible with these classical computers. Maybe after 70, 80, or 100 years, quantum computing might be at the desktop of every northern person, but as far as the complexity and all those things of quantum computing are considered, I'm not sure that we'll be doing all those day-to-day work over here on quantum computers. Yeah.
Thank you.
I hope I answered the question. Yeah.
Yes. Thank you very much.
We have one question from Saad. Is that
Yes,
what are your views on the privacy violation due to the quantum computing, as you said that it would take only 15 minutes to decrypt any kind of encryption?
Yeah, this was a statement given in the article which was published by Boeing on their quantum computers. Yes, this is like the alarming condition for everybody in the world. So that is why, first of all, like third world countries are not very much, welcome in doing quantum computing on those areas. There are just few people who have done, like Dr. Sabi Anwar is one of the graduates of, Oxford University, who have his PhD in quantum information, etc. So there are very small number of people who are doing, getting all those technologies from there. So these are the major concerns. Even the Western countries, all those, they have this question mark over there in the progress of quantum computing, because nothing will be secure anymore.
We are going towards the last speaker of this session. He is Dr. Syed Atif Mahdi. He received his PhD in robotics from University of Kaiserslautern, Germany. During his PhD, his focus was on developing learning strategies for an indoor autonomous mobile robot to determine the presence of an elderly person in home environment. He was also responsible for the development of an autonomous octocopter that can perform various inspection tasks in field environment. He also worked on development of an autonomous low-speed tractor that can work in an agriculture field. Since 2016, he is an assistant professor at University of Central Punjab, Lahore. He is also the director of Center of Robotics and patron of IEEE University of Central Punjab Student Branch. His research interest lies in development of autonomous robots that can perceive environments around them and perform various tasks according to the dynamics of a situation. So over to Dr. Syed Atif Mehdi.
Thank you very much, Tanveer, for a very elaborative introduction. And thank you, everybody, for a very nice talk. Dr. Wajahat, Dr. Robert, and all others. So it was a very interesting talk. So my talk is a little bit towards the application of the artificial intelligence, and especially in the area of robotics. I hope everybody can see the slides. Are they visible?
Yes, these
Yes.
are
Yes.
visible to us.
Very good. Great. So my talk is actually robots in agriculture, and my name is Dr. Syed Atif Mehdi. I'm of Center of Robotics at University of Central Punjab. So brief overview of myself. So anybody who would like to contact me, they can contact me at my email address. I would like to share some Center of Robotics. So we have 5 faculty members associated with the Center of Robotics. Myself, Dr. Musharraf Hanif, Dr. Yasir Niaz, Dr. Umair Nasir, and Dr. Zubair Aftab. So we have 2 researchers, Amir Asghar Ali and Hamza Muzammil. They are full-time researchers at the lab, and we have more than 25 bachelor's and master's students who are working in development of different kinds of robots, especially for the agriculture. And here you can see some views of my lab, where some people are working on their projects. The Center of Robotics focuses on solving real-life challenges, and we are in the area of developing autonomous robots that can be remotely operated as well, and they can perform different tasks on their own. Our main focus and development of these robots is towards the agriculture. We will come to that. But more recently, you have been seeing autonomous robots being developed for agriculture. Some of them are still in development. For example, this particular robot, the upper left corner robots, this is a swarm of robots, and their task will be inspection of the field, preparing of the field, and then at the later stage, maybe harvesting of the field. On the top right corner and the bottom left corner, these are the robots from Harper, Adams University from England, and I will show you their videos in a few moments. And of course, besides these ground vehicles, a lot of people are working in the area of flying vehicles, drones that can hover or fly over the field and can do a variety of tasks. So let me show you one of the videos from Adam Harper's University, England, where the robot is working, robots are working autonomously, and the intelligence in the field, in an agriculture field. And here you can see a lot of sensors that are being installed on the tractor. And the main reason for these sensors is that with these sensors, the machine can actually comprehend the environment and move according to the plans. So here you can see how the ground is being made for a new harvest, for a new crop. The good part of these autonomous machines is that they can work in day and as well as night. So for the farmer's point of view, it's a great relief that he just have to push the button and the machine is doing all the work for the farmer. So on one morning, the farmer can come to the farm, push the button, and can go away for a party or whatever. And then the next day, when he will be there, and the field will be completely ready. So this is the future that we are looking forward. Focus on agriculture is because Pakistan is an agriculture country. About 70% of its population is directly or indirectly related to agriculture. The main income source for these people is coming from the agriculture produce, agriculture byproducts, and things like that. and this accounts for 21% of GDP of Pakistan. However, our production from per hectare yield is between 29% to 52%, which is far low than the world best averages. So this needs to be improved. And one of the things that you can see in the picture below is that traditionally we are still spraying by human beings. So our fields are being sprayed by the human beings. So they go in the field, they take up this tank, they move in the farm. And as you can see also in the picture, that people are not even wearing protective gears. So this is quite hazardous. And on the right side, you can see the effect of fungus on cotton. So cotton is one of our export crop. And when the fungus is infested in the field, it destroyed the field completely. And the brown plants, all those you can see, they are infected by the fungus. So with the project, the title of the project was Detection of Fungus in Fields Using Autonomous Robots. This is a collaborative work between University of Central Punjab and University of Cotton and Greenworks. Greenworks is our local partner in Lahore. University of Qazi is in Germany. And this project was funded by DARD Germany. DARD is like HSC of Higher Education Commission of Pakistan. Starting the detection of fungus was that especially the breadless. This is the flower that you see in the bouquet. When you buy a bouquet, you see a very long stem flower right at the back. So this is a flower that is not native to Pakistan. All the seeds and the bulbs, they are imported from Holland. Greenworks is one of the companies in Pakistan that they import the seeds and they distribute these seeds among the farmers. So from one bulb, one flower can be grown. And the good thing is that once you have harvested a crop, you can save the seed, and the seed or the bulb can be used next year again for the flower. So this cycle can go up to 5 years, and five yields can be taken from one bulb. Since this plant is not native, it is prone to a lot of diseases in Pakistan. One of the disease is fungus. So we started our initial work in 2016 in collaboration with Greenworks, and formally we started the project in January 2017. In Pakistan, in Lahore, around Lahore, the gladiolis is sown around October, and it is harvested around February. So a field that was around 70 kilometers away from University of Central Punjab. So this is the overview of the field. This is about a 2.5 acre land, and here they grow gladiolis regularly. So we went to the field and inspected how the fungus is infecting the plants. And the picture on the left, you can see a very healthy plant. The bulb is very healthy, the stem is very healthy, the leaves are very healthy. And on the left of the first picture, you can see fungus infected plants. And here you can see that the leaves are palish, yellowish color, brownish in color, and the bulb is almost completely destroyed. So in the picture number 2 and 3, you can see how the bulb is being destroyed. So once the bulb is destroyed, it cannot be regrown the next year. So it is a loss for the farmer. So what we did was we did aerial imagery of the field. For data collection, we performed surveys, field surveys. We interviewed farmers, and based on our compliance, we developed our image processing based algorithms to detect fungus in the plants. But for an autonomous inspection of the plant, we need to have full area coverage of the field, and for that we have developed our own path planning algorithm. So with this path planning algorithm, we can only give commands to the copter to take off, and then the field is the robot, drone, it performs the path planning for full area coverage and full field inspection, and then it flies on own using waypoint navigation. So before going to the field, we performed our experiments in simulation. We developed a simulation environment, and here we performed our simulations. The real field. Here you can see the atlas is being shown. So this is the first of all the manual control of the copter. So the copter is flown by using the remote buttons, and with this you can see how we can see that simulation is working. Then we performed this using autonomous navigation. Now the autonomous navigation is working, and here you can see that the plants who are yellowish in color are being detected as fungus infected plants. So with this progress, we were in the field, and we just pressed the button, and the copter took off, and it is going autonomously in the field. It has planned the path, and now it is taking the pictures. So over here, you can see that on the left side, the original images are coming, and on the right side, the detection algorithms are working. And this is a very healthy crop, and now this is a highly devastated crop where a lot of plants were hit by fungus. It was a great loss for the farmer, but for us it was good that we were able to generate a good data set, and we can actually prove that our algorithm was working fine. And here you see that red parts are the since it was a experiment, we performed another task that with the imagery, we can actually see that how many plants are there. So we also did the plant counting, and we can now give information to the farmer that he has sown, for example, 80,000 of the seeds, and how many plants have grown up from these 80,000 seeds. So this is my group on the field. So with this project, we have another project that was related to this flying of the copter. So this is a real field experiment, and this is a huge copter. This is an hexacopter that was flown by professionals. And here you can see how the flight place. So let me back. Any guess? Main issue was that it was not a good flight, and it seemed that the copter has almost hit the ground, and it was extremely bad. Luckily, bad went, and it took off afterwards. From this, we come up with an idea that okay, this is not a good start. And even the experts, when they fly copters, they sometimes make mistakes. So with that, we move to the idea that how the copters should be flown. And we come up with some initial ideas that, okay, how about wearing a glove and then communicating with the copter, and controlling the copter using the hand gestures by wearing these gloves. This was not approved because the farmers who are working in the field, they have usually very dirty hands, and they also do not like to wear gloves in the field when the temperature is 43 degrees centigrade outside. So here is also another area where the drone camera is looking towards the human being, and with the commands of the hand gestures, it recognizes what task to perform. Again, this was not favorable for us because we want to see the crop. So the camera of the drone should see the crop and should not be looking towards a human being. And also, if we have this mechanism, range is very limited. So we cannot go into the field with saying that, okay, this copter will be controlled by a human hand and still be working in the area. So we come up with another idea that, okay, we develop a hand gesture-based control architecture where the gestures are being acquired by one camera and the commands are transferred through Wi-Fi to the copter, and the copter performs the task. So we did the gesture acquisition and gesture recognition task. So this is the TensorFlow architecture where we have convolution layer, ReLU layers, and from this we have fully connected networks. And at the end, when a gesture is performed, we know which gesture has been performed. And before taking this to the field, we performed this university. So over here at the bottom right corner, you see that the camera is placed at the far away from the copter. The copter is right in the center of the university, and the commands are being transmitted once they are being detected by the cameras over here. So here you can see the takeoff command has been given. The copter takes off, and when it reaches a specific height, it stops. And then left command is given, and then the right command is given. Right. So forward, backward, so all these commands are being recognized far away from the copter. And the task of the copter is then to inspect the field and prepare data set or prepare imagery for the field. And for example, if the farmer performs a down command, if it is less than 7 feet, it will not go. It will not land. For landing, there is a special command. This is for protection. So, if the farmer is unconsciously performed a command to land, it may not be fulfilled. So from here, I want to move towards different aspects of robotics. Here's our project was intelligence and autonomy extension for low-cost freshwater inspection vehicle. So this is a collaboration between University of Central Punjab, Jacobs University, Germany, and ITU University, Lahore. And again, this project was funded by DRD. So our motivation, this project was that there are a lot of underwater vehicles available in the market, and they can perform a lot of very interesting tasks. But somehow these are very expensive vehicles. So we wanted to develop a low-cost vehicle with a modular design, with the base design, which can perform autonomous navigation, which can also be guided through remote controls, and it can be used for inspection of canals. As you already know, we have a huge network in Pakistan. We have a huge network of canals, and we want to see what is in there, the types of fish, and the pH of water, the total dissolved solvents of in the water. So such kind of experimentations, we wanted to have those results. So for that, we have gone through a lot of physical designs. That should be a combination of propellers that can be used. And here were some suggestions. So one configuration was that we may have two propellers which may be thrusting the robot forward, and two propellers which can be used for up and down motion. Or 6 propeller combination, and 3 propeller combination, and all those things. But for that, now we have a combination of 6 propellers, where 2 propellers are for upward and downward motion, and 4 propellers are for 6 degrees of freedom. We performed orientations. We want to find that, okay, if we place thrusters in particular direction. So the thrust of one thruster should not be in the wake of the other thruster. So we performed NSYS simulations, and here are some of the results where we can see that how the thrusters are being performed, and what should be the orientation of the thrusters. And in the bottom layer, you can see that the left picture shows the velocity of the thrusters when it is moving, and how much water it is throwing backwards. The green area shows the comfort level of the thruster, and also on the right, if there is turbulence. For example, the waves are moving, what is the turbulence level and how the thrusters are moving. So we perform these thruster. Then comes the design of the frame panel. We again performed the structural analysis. We designed the structure, performed the structural analysis on the NSYS part, and here we can see that our main structure is quite capable of holding a lot of pressure. The weak parts are marked in red, but the pressure over here is extremely high, and still the structure can survive. So we are hoping that our underwater robot can go at a depth of around 10 meters. So, but at the moment we are hoping for only 5-meter depth, more than that. So it is very good range. So here you can see the assembly parts. So this is a tube which will contain all the electronics, and on the right side you will see the structure, the low-cost structure that we have. And here is one of the simulation we have developed. Again, you can. This is very interesting simulation. If if some people may look at it, they may say that okay, this is similar to Finding Nemo, the movie Finding Nemo. But this is a simulation that our research group has developed. This has been developed in Unreal Engine. And you can see over here, for example, let me just pause it. So the effect of lightning that is over here, the movement of the fish, the clarity, this is extraordinary. So the engine, most of the people know Unreal Engine from PUBG. So the game has been developed in Unreal Engine, but we have made better use of it. Okay, for us, it is a better use that we can have a very good simulation from here. And here you can see the are moving, and the areas, the bubbles that are coming out of the ocean, they are very interesting. Right. So since this simulation is developed, we developed a robotic simulation as well, where one of the robot can go in the water in simulation again and see what's going on. So here is the view of the robot. You can see the camera that is viewing, and on the right, this is a robot. It is wire. You can also see wire connection over here, but this is all in simulation. So we can actually see what the camera, what is underwater, what are the structure, what kind of fishes are moving in front of the robot, and we can also move the robot in different directions. So this is Unreal Engine, and then again at the back we have a ROS robot system that is working for us. Actually specify water pressure or water waves and things like that. I would like to thank you all, and here is a robot that we have developed. Somehow it is in different view. I hope you may. So this is about us who are not doing exercises. We can reduce our calories using this robot.
You Thank you, Dr. Sayyid Atif Mehdi. That was an informative task. Thank you, Dr. Sayyid Atif Mehdi. That was an informative talk from your side. If someone has question, he or she can ask. Let me invite Mr. Ali Azaz. He's a director admissions, and he will be concluding the session with concluding remarks on behalf of University of South Asia.
Thank you very much, Tanveer. Let me start. Can you give me the option of sharing the screen so I can share the screen?
Presenter rights has been shared.
You have access now. You have access now.
Okay, I have the access. Let me.
I will request our speakers to please start your video so we can have the group photo.
Tanveer, can you take a screenshot on my behalf? First of all, before concluding this session and before thanking you all, let me tell all of you about University of South Asia, from which me and Tanveer Sahab is. University of South Asia is one of the prominent and very reputed private university in Lahore, Pakistan, and we have been working since 2005. It's a provincial charter, and we have 3 campuses in Lahore in different situations, and we have a student body of more than 5,000 and a faculty of more than 300 scholars. Coming back, this session was initiated with the collaboration of IEEE and ACM, and it was an initiative of our very dear faculty member, very dear colleague, Mr. Sayyid Tanveer Bukhari. And on the behalf of University of South Asia's management, I would like to thank each and every one of you, especially people from abroad and even from Pakistan, because I know there have been, time differences, and you people have given your precious time, especially Mr. Hamza has been hosting this session, Mr. Andrew, Dr. Wajahat Qazi, Dr. Atif, Dr. Joe. You have all given very, calculative and very informative webinars in your specific field. And my favorite one was, obviously every webinar was favorite, but Mr. Andrew's personal reflection was very heart-touching and very detailed one. I believe that internet has made this world a global village, which it's an old quote, but it has really, in these testing times of COVID, we have come across we have come across all the way so long that we are very isolated in our homes, but we are all connected. This is, I believe, a blessing in disguise. So by using this platform of IEEE, I once again thank you, all of you, for giving your precious time. Your honorable words and your time has definitely benefited many throughout the globe. You on the page by the live stream on the page of IEEE Lahore, and the live stream on the page of University of South Asia's Lahore as well. Once again, Dr. Atif, Dr. Wajahat, Dr. Bishop, Dr. Andrew, it was really nice meeting you. And obviously, this virtual meeting is the new normal nowadays. I've shared my LinkedIn profile in the chat box as well. Would like to connect with all of you. And once again, thank you very much. I would request Dr. Wajahat Qazi and Mr. Hamza as well to turn on your cameras for the digital selfie, so we can have a memory and we can post it over University of South Asia's page as well. Dr. Wajahat, can you hear me? Thank you.
Hamza, did you took the
Yes, I'm starting my
digital group photo?
Yeah, for sure.
Okay. So let's have our cameras, screens on the screen. Can you see all the participants on your side?
Yes. So thumbs up to all of you. Thank you all for joining. Teacher Dan.
I think it's time to say bye-bye, Andrew and
Was
Bishop.
everyone
So we'll
in the
be seeing
picture?
you sometimes in future. Yeah.
Was everyone in the image?
Yes, I think so.
Yes, I took the picture in grid mode.
Dr. Andrew?
Thank you.
Yeah, I watched it on Facebook. It came through very well.
All right, Andrew. So I think it's time to say bye-bye to everybody.
Yeah, and see you soon, hopefully.
Yeah.
Thank you very much. It was nice meeting you all.
Yep. Bye.
Thank you. Diolch yn fawr.
Bye bye.
All be there.